The Earth is not a perfect sphere. Its physical reality is an oblate spheroid. Centrifugal forces slightly flatten the poles. This 0.3% compression means the polar diameter is 43 kilometers shorter than the equator. Satellite measurements reveal an additional distortion. The planet is slightly pear-shaped, with its maximum diameter sitting just south of the equator. Because of these physical irregularities, mapmakers rely on geodesy to build local datums. The UK uses a 1936 model called OS-36, while France maps to NTF-70. Local datums work on paper, but they break down inside modern flight management systems. Comparing a UK beacon against a French beacon, an aircraft can calculate a sudden position error of up to 200 meters over the English Channel. To eliminate these boundary errors, the International Civil Aviation Organization adopted a single universal standard for GPS, the World Geodetic System 1984. Navigation computers handle that complex WGS-84 geometry automatically. But when a pilot does the math by hand, those equations are far too complex. For the EASA and DGCA exams, you apply a strict mathematical baseline. As this table shows, you must assume the Earth is a perfect sphere, with a circumference of exactly 21,600 nautical miles. To navigate this sphere, we need a grid, and to orient a grid on a floating object in space, we first require an absolute reference point. That reference point is derived from the Earth's spin. The absolute extremities of this rotation define the polar axis. This graphic maps the cardinal points based on the planet's rotation. Because the Earth continuously spins eastward, it provides fixed, absolute datums for true north and true south. Traditional maritime navigation relied on cardinal and quadrantal points like northwest or southeast. At aircraft speeds, that system lacks the necessary precision. Here we see the instrument layout for the sexagesimal system. Aviation measures direction as a continuous 360-degree clockwise rotation starting from north. This requires strict discipline on the radio. True direction is always written and spoken as a 3-digit group. 90 degrees is a dangerous ambiguity. The standard dictates 090 degrees true. The most important geometric feature on this sphere is the great circle. A great circle is any circle on the surface whose center and radius exactly match the center and radius of the Earth itself. If you select any 2 points on the globe, the absolute shortest ground track between them is always the shorter arc of the great circle that connects them. Every other circle on the planet is a small circle. These are planes that slice through the Earth but do not intersect the exact center of the core. The single great circle sitting exactly 90 degrees perpendicular to the polar axis is the equator. This serves as the 0-degree datum for measuring latitude. The 0-degree datum for longitude is the prime meridian passing through Greenwich, which is a semi-great circle connecting the poles. Moving north or south from the equator, every parallel of latitude is geometrically defined as a small circle. Together, these intersecting circles form the graticule. This effectively replaces a flat, 2D Cartesian plane with a spherical grid based entirely on angular measurement. Meridians are the vertical lines of this graticule. They are semi-great circles joining the north and south poles. By strict geometric definition, every single meridian intersects the equator at exactly 90 degrees. If the Earth were a perfect sphere, defining the angle of latitude from the equator would be straightforward. But the physical compression at the poles creates a mathematical anomaly. If you measure an angle directly from the Earth's true physical center up to a point on the surface, you get the geocentric latitude. Because the surface is flatter near the poles, a line dropped perfectly perpendicular to the local surface curve will miss the Earth's core. The angle this perpendicular line makes with the equator is the geodetic latitude. This angular difference reaches its maximum exactly halfway to the poles. At 45 degrees north or south, the geocentric and geodetic latitudes diverge by exactly 11.6 minutes of arc. Earth's 23.5-degree axial tilt also dictates 4 special parallels based on solar position, the tropics of Cancer and Capricorn, and the Arctic and Antarctic circles. Because aircraft fly relative to the physical terrain rather than the theoretical core, all aviation charts and flight management systems exclusively plot geodetic latitude. Looking down at the North Pole in this diagram, we see the mechanics of longitude. It is defined strictly as the shorter arc measured along the equator from the prime meridian to your target meridian. Because it is always the shorter arc, longitude extends exactly 180 degrees east and 180 degrees west, meeting precisely at the Greenwich anti-meridian. Calculating the change in longitude between 2 points in opposite hemispheres requires checking that 180-degree boundary. Take 163 degrees east and 152 degrees west. Adding them gives 315 degrees of total arc. Subtracting that 315 from a full 360-degree circle reveals the shortest path, a 45-degree change in longitude. To fly a route, pilots must translate these abstract angular measurements into physical distance over the ground. This conversion relies on one mathematical constant. Exactly 1 minute of arc measured exclusively along a meridian is equal to exactly 1 nautical mile. When entering coordinates into a navigation computer, the format of the numbers tells the system exactly what level of accuracy you are claiming. In this resolution table, the format 5321N uses whole minutes, specifying a 1 nautical mile accuracy. Adding a decimal steps up to FMS precision, narrowing the error to 600 feet. Sub-minute decimal seconds yield landing calibration levels, locking the position to 30 centimeters. This geometric consistency applies globally. If you follow a great circle track to its northernmost vertex, the exact opposite point on the globe maintains the identical latitude number, simply inverting the hemisphere and the longitude. The planet is an immense, irregular shape. Mastering these strict geometric axioms provides the only mathematical framework capable of delivering absolute real-world accuracy anywhere on Earth.